Welcome everyone to the last part of my video series on Archimedes on the sphere and cylinder. So far we've seen Archimedes derive formulas for the surface area of cylinders, isosceles cones and spheres, and also for the volume of a sphere. And now we'll look at how he tackled what you get when a plane cuts through a sphere. He called these bits segments of a sphere, and I'm going to do the same, but I should point out that nowadays lots of people call these shapes spherical caps and actually use spherical segment differently for a bit of a sphere that's cut off between a pair of planes. So please don't get confused. In the terminology we're using just for this video, there's just one plane involved in creating a spherical segment. We're going to start with the surface area of a spherical segment and the volume of a spherical sector. And because the methods here are so similar to what we've gone through for spheres in their entirety, I'm just going to sketch things out and challenge you to fill in some of the details. So to calculate the surface area of a sphere's segment, start with a circle segment sandwiched between polygons that have some even number of equal sides along with their base. And for simplicity, I'm just going to focus in the diagram on the inscribed shape, but you have to imagine a circumscribed one with the same number of sides. We rotate the whole diagram, pair off the sides into horizontal levels, and in each level use the formula for the surface area of a cone slice or a cone at the top and try and add them up. And what we find is that the total surface area of the inscribed shape will be pi times the side length times the sum of these horizontal chords just using half of the base. And to work out that sum, we introduce a zigzag of similar triangles to see that those horizontal chords and half the base are to the height of the segment as SP is to NP. So that means that the inscribed surface area is pi times the height of the segment times PS, in other words, just a little bit less than pi times the height times the diameter of the sphere. Similarly, when we look at the circumscribed shape, which is the inscribed one that's just dilated a bit, that's going to turn out to be slightly more than that same value, pi times the height times the diameter of the sphere. You have to be a little bit careful about justifying why the circumscribed surface area is bigger than the spherical one, even though they don't have the same edges. But what I'd recommend is you can introduce a sort of intermediary shape by just kinking the outer side in the polygon in to be tangent to the circle, and then you imagine that intermediary shape also being rotated. Show that that's in the middle of the circumscribed shape and the sphere. Now, if you can get all that to work, we can reason that the only value left for the surface area of the segment itself is pi times the height times the diameter of the sphere. And moreover, the height of the segment multiplied by the diameter of the circle it's cut from is also the square of NA, because after all, NA to NX is the same as NS to NA by similar triangles. So Archimedes discovered that the surface area of a spherical segment is equal to a circle whose radius runs from the center to the edge of the surface. So we've got two formulas, and we can use whichever is easiest, either pi s squared, s for sort of side, the oblique side, or 2 pi times the height times the radius. And the latter, for example, is a good one to use for the following beautiful result, which you might like to pause and try. When a sphere nestles inside a cylinder, so it's touching the cylinder on all sides, any slice that we can take out of that arrangement using two horizontal planes, planes perpendicular to the axis, so horizontal the way I've drawn it, that will have the same area of spherical surface as it does of cylindrical surface. So have a go at that one. Moving on to the volume of spherical sectors. Again, we sandwich a circle sector, decompose the polygons that we've got into triangles, much like we did when we were finding the volume of the sphere as a whole. And when we rotate that arrangement, what we're going to get is a set of rhombs, that kind of spinning top shape that we talked about in the last video, and differences between rhombs. And for each rhomb, we equate its volume with that of a cone of a fixed height, namely the distance from the center to the edges of the polygon. And the bases at each level work out to be the same as the surface area of the cone slice produced by the edge in each horizontal level of the diagram. So again, pause the video and just check that you can take these arguments that we've used, apply them to this case, and show that the overall volume of a spherical sector is that of a cone whose base is the outer surface of the sector and whose height is the radius. So if you want to put that in modern terms, that's going to be pi times s squared times r over 3, or 2 pi times h times r squared over 3, if you remember the s, r and h that we introduced before. So those processes so far are so similar to what we've done with the sphere as a whole that I've just sketched out the method and left some of the details for you to fill in. What we're going to do next is look in some more detail at how Archimedes develops these results in some further problems about spherical segments. And the first of the three we're going to look at is, what is the ratio of a spherical segment to the cone that you can inscribe inside it? So if we start by focusing on segments that are less than a hemisphere, what we've got effectively is a sector, so joining up to the center, minus a cone. And cones are so important for what Archimedes is going to do and the way he's thinking about these problems that I'm going to introduce some special notation to describe a cone with a certain base radius like xa and height xo. We'll write that just as c xa xo. So that's how to read that notation. We've seen that the whole sector has a volume that is equal to a cone, namely the cone NaNo, right? The height of the radius and the base equal to pi times Na squared, as we were just describing a minute ago. How can we compare those two things, C xa xo and C NaNo? What we need to do is get a handle on Na squared to Xa squared, and we use similar triangles. Na to Xa equals Ns to As and also As to Sx, so we can multiply those two things together. And we see that that ratio is Ns to Sx. So that means we can rewrite CNaNO as Cxa NO times Ns to Sx. And this allows us to get a formula for the segment, the difference between these two cones, which we've now described in terms of cones, both of which have a base radius xa. Now, it's not a very pleasant expression, but if we unpack it and do some fairly basic algebra to the expression for the height of this cone, what we find is it reduces to nx times no plus xs over sx. So that allows us to conclude that the ratio of the segment to its inscribed cone, which is C xa and x, can be described using this ratio NO, the radius, plus Sx to Sx. Now, we can look at the larger segment in exactly the same way and find that its ratio to its inscribed cone is equal to the analogous formula SO plus NX to NX. I'll leave that as an exercise for you. It is just slightly different because that segment is larger than a hemisphere. Now, this way of comparing the volume of segments to inscribed cones allows us to calculate the ratio of the larger to the smaller segment if we know how far along the diameter we've cut. So you might like to check that you can use the formulas we've discussed to find the ratio of the volumes when we cut the axis a third of the way down, for example, where nx is 2 and the radius is 3. And hopefully you'll find that the ratio of the segments comes out to a ratio of 7 to 20. But what about the converse problem? Suppose we have a sphere that we want to share in some given ratio, like 2 to 1. How do we work out where to cut? This is a simple problem to state, but it's deceptively difficult to solve. Suppose the ratio that we're after is described as 1 to lambda. Using the formulas that we've seen so far, we get a rather ugly expression like this. And what Archimedes does is some groundwork to simplify things. And I'm going to do something similar, which is in fact even simpler than the method that Archimedes used. So we look at this and we say, well, ax squared is nx times sx. So this is a famous circle theorem. So the southern segment can also be written as c sx so plus nx. So we've just slightly manipulated the formula for the segment in terms of a cone. Now, a very neat way then to get rid of some of the terms involving x, the unknown, is to consider the southern segment not against the northern segment, but against the whole sphere, whose volume, as we've seen in the previous video, can be described as the cone whose base radius is the diameter and whose height is the radius. C, ns, no. So we need to find x on ns such that sx squared times so plus nx is equal to ns squared times no times lambda to 1 plus lambda. And the nice thing about that expression is that everything on the right-hand side of the equals has been given by the terms of the problem. So if we look at this with modern eyes, we would say something like, well, so plus nx, that is 3 times the radius minus sx, which is a variable. So we've got an unknown and we have a cubic expression, cubic polynomial, that we need to solve. And using techniques developed in the 16th century, you could solve that and get an exact solution for sx in terms of the radius and that parameter lambda that we've been given. But in general, solutions like that are not going to produce lengths that can be constructed using the traditional Euclidean tools of just a straight edge and a pair of compasses. So what the Greeks did in such a scenario is not try and solve cubic equations, which they didn't think in terms of. They allowed themselves an extra ability, which is the ability to draw conic sections. So let's look at how that works. And for this, I'm just going to state without proof a couple of basic properties of conics that we're going to need to be aware of to understand what follows. So first of all, in a hyperbola, if you take pairs of lines drawn in parallel from 2 points on the hyperbola to the asymptotes of the hyperbola, then those lines have the same product no matter what point they're drawn from. And here we're just going to need the simplest case, which is where the asymptotes are perpendicular to each other and the lines drawn from the points are parallel to the asymptotes. Secondly, we need a basic property of a parabola. Say we've got a vertical axis of symmetry, then the square of the horizontal distance from the parabola to the axis is a constant multiple, a kind of coefficient if you like, of the vertical distance along the axis. Now, the construction that seems likely to go back to Archimedes, going back to our sphere sharing problem, starts by adding the radius sz onto the south pole of the sphere. And what we then do is attach a length of the radius multiplied by lambda to 1 plus lambda at right angles from z. So that's ZO, and we complete the rectangle ZNHO. So going back to what we established before, what we're going to look for is to find the x such that nx squared times xz, which is the radius plus xs, of course, is equal to ns squared, diameter squared, times nh, the radius, multiplied by lambda to 1 plus lambda. Now, in fact, Archimedes does something a bit more general here. He replaces ns squared with the rectangle defined by nz as one side and a variable length hm as the other side. We can set hm to ns squared over nz, 4/3 of the radius, and that will solve the specific problem of cutting the sphere that has ns as its diameter. So we use OH and OZ extended as the asymptotes and draw the hyperbola with those asymptotes that passes through n. There is only one. And then we imagine a family of parabolas that pass through H and have Hn as their axis of symmetry. And we use Hm as the coefficient, so the value of the square of the vertical distance of a point from the axis to the horizontal distance of the point from OH. Now, suppose that the hyperbola and the parabola meet at y and drop the perpendicular to nz and then beyond it to HO. Because y is on the parabola, we can say nx squared to yw is equal to hm. And since y is also on the hyperbola, we can say that zx times yw is equal to nz times hn. So overall, we have that nx squared times zx is equal to nh times nz times hm, which is what we wanted. Remember that we can set hm to any particular value that we want, in our case to make nz times hm equal to ns squared. And that stuff that we did about y there, we weren't fussy about where the conics meet. So if they meet in two places, y and y1, we also immediately have that nx squared times zx will be equal to nx1 squared times zx1. And a neat feature of this is that as we increase hm, the parabola gets wider and wider, and eventually we'll reach the largest value of hm for which there is a solution at all, which is when the parabola is just externally tangent to the hyperbola. And Archimedes seems to have used some slightly more advanced results about conic sections to produce actually quite a neat geometrical way of finding the x for which the value nx squared times zx is maximized, which turns out to be at s. But that is a story for another video, if I have time in the future. So I've got another challenge for you at this point, which is to work through a different solution of the sphere sharing problem. So same problem, different solution by a mathematician called Dionysiodorus. And he seems to have lived about a generation or two after Archimedes. He adds the radius on at the North Pole instead, and at the tangent from the North Pole, he marks off NH, which is the special length that we used in Archimedes' proof as well. And we also mark off NG, which is the geometric mean of NH and the radius. And then we draw the hyperbola through H, with these lines through S as the asymptotes, and the parabola with axis ZS that passes through Z and G. And the challenge is to show, using the same basic properties of the parabola and the hyperbola, this is what I'm asking you to have a practice with, that those two curves intersect at a point y next to the circle, such that the plane through y perpendicular to NS is the right place to cut the sphere, so that the segments have the ratio of lambda to 1 to each other. Now, the third and final problem that we're going to look at, based on Archimedes' study of spherical segments, is to show that of all the spherical segments whose curved surface is a given size, the hemisphere is the one that has the largest volume. Suppose we've got the hemisphere and some other segment, as in the diagram. What can we say straight away from the fact that the curved surface areas are the same? Well, it's that NA is equal to N dash A dash, because remember the surface area we saw is the same as a circle whose radius runs from the middle to the rim of the segment. Now, the volume of the hemisphere, which is also, as well as being a segment, is a spherical sector, has a nice simple formula. The cone with base radius N dash A dash, height N O dash. And we've already seen a couple of formulas for the volume of the upper segment. One of them is CAX and then NX times NO plus SX to SX. The other one, which is nice and simple, is CNX NO plus SX. But again, we can use simple similar triangles and get yet another one, which is, well, we've got NA squared to AX squared is equal to NS to SX. So we can use that to transform this formula into C of Na, and then nx times no plus sx to ns. So we need to show, in other words, now that we've got two cones with the same base radius to try and compare, we need to show that no dash times ns is greater than nx times no plus xs. And the key point here is that no dash, if we look over at the hemisphere, is equal to n dash a dash squared over 2, which, going back to the other image, is na squared over 2. Na we know is nx times ns, so na squared over 2, na squared is that, so na squared over 2 is going to be nx times the radius. So not only can we subtract one of the terms here and focus on showing that no dash times o dash s is greater than nx times xs whenever x isn't at the centre, but also is familiar from book 2 of Euclid's Elements that that inequality is equivalent to no dash, well, to o dash being between x and o. And it clearly is because, as we've just seen, no dash is actually the geometric mean of nx and no. So this completes the proof. Well, I hope you've enjoyed this series on Archimedes on the sphere and cylinder. It's such a rich work. It's got both these very important results that we think of nowadays as absolutely basic formulas that we teach people in school, but it also has some really quite complex operations exploring the properties of spherical segments. Do please check out other videos on my channel, and thank you very much for watching.